Hello and welcome back. Today we're going to continue talking about categorical data and how we analyze it using our the data that we have from the Titanic. I'm actually really excited because today we get to talk about independence, and this is going to be really cool. Just had some really fun breakthroughs connecting stuff from the very last chapter of the textbook to what we're doing now, which is just in the second chapter of the textbook. And I'm going to show it to you just as a teaser so you can see what we can do with the power of statistics. And this is actually stuff that we were talking about with Kristen Gilbert, but now we're going to apply it to the Titanic and some other cool data, even your data. Yes, your data. So today, if you can't tell, I'm way too excited. So hopefully you watch this video all the way through and you feed off of my enthusiasm. So the first thing, not as exciting, but we want to talk about ways that we can break down a contingency table. So a contingency table is when we're looking at breaking down cases by two variables. So in this case, our two variables are class and survival. So the contingency part is, where do you sort out between those two things? What was the class that you were a part of, and what did you survive or not? So you'll see these 8 pieces of data here. That's the actual counts or the data that's being sorted out in the contingency table, right? So there were 203 first class survivors and there were 122 first class non-survivors. I don't know, it's really depressing. I don't want to talk about that. All right, so anyway, that's just the contingency table, but this is a special contingency table that gives us all the different frequencies or all the different proportions, not frequencies, but all the different proportions that we could have, the contingencies. Or conditions, I guess is the right word for it. So let's look at our first one. So the first one is the percentage of the row. So if we look here on the row, that's 100%. So we're talking about what is our breakdown of all the survivors. So if you survived, we're only looking at this row, what was the class breakdown by by survivors? So of all the survivors, 28.6% were first class, 16.6% were second, 25% were third class, and you can read that in crew. And altogether that gives us 100%. So what is the class breakdown of those that did not survive? Oh, I said the D word, sorry. And you can see this giant percent, the 45% of all the people that died were from the crew. Right, so that's a lot. Anyway, so that is the second way we could break it down, by a percentage of whether or not you survive, so conditional on survival. And then the next one is the percent. Did I do that one? No. Yeah, this is our next one. I'm sorry. Percent of the column. So now our 100% is in the column. So of all the first class people, what is the proportions or the distribution of survival across the class? So what's the survival rate for first class? So 62% of all first class people survived, meaning the complement of that, that's the word I was looking for. Anyway, the complement of that would be the death rate, right? So if 41% of second class survive, that means the complement, or 1 minus that value, or 100 minus that, if we're looking at percentages, would be the death rate. So the survival rate was 25%, so close to 75%. See how this works? 25%, 75%, you get the whole thing. All right, the other one is the percent of the table. This one is almost never used. So of all the people who were on the Titanic, what percent were first class survivors? What percent were first class non-survivors, etc.? We rarely ever use that one. The one we're really interested is going to be the percent of the rows and the percent of the columns. So the death rates and of those who survived, what was the distribution of the classes? Anyway, and whenever we graph those percentages across here, or the percentages across here, we get some really cool data, and it allows us to visually see whether or not we believe that these two are independent. Sorry, I spent a lot of time on this slide. We're going to move right along. All right, so conditional distributions, but a percentage of what? So the overall, where you see the 100%, that's going to be the distribution of the total. So 9.2% were first class survivors. That's the one we don't use very much. Okay, also if we look over here, the 100% are here. So that's going to be of all the people who survived. This is the percent of the class distribution of survivors. This is the class distribution of the non-survivors. Okay, and then down here, if we look at this class distribution of survivors and non-survivors, and we graph out those percentages in a pie chart, boom, what do you see? So what are you noticing when we're comparing the distribution of class for survivors and the distribution of class for those who died? The question we would have is, are those two similar? Now, we wouldn't expect them to be exactly the same. For instance, if this was 40% of crew members, of those who died, 40% were crew, we wouldn't expect exactly 40% of the survivors to be crew, because there's going to be variation. And in all statistics and sampling, there's always variation. But are these far enough different from each other that we think that they're no longer independent? That's the real question that we're trying to answer. So are these two distributions of survival and death, are they different enough for you to believe that they are not independent? And then the real question, where it gets really cool, is how do you quantify that? So it's not just an objective, or sorry, it's not just subjective of how you feel. Well, I think that's different enough for me. We can actually quantify that with probability, which we'll learn how to do in this course. All right, so as we showed here, this is the distribution of the death rates or survival rates. Both of those are graphed out. So survival rates here, distribution of those, not survival rates, I'm sorry, distribution of class by those who survived. And then on the right here, we have the distribution of class by from all the people who died. Then that helps us, we can compare to see if we think they're independent, if those are similar enough. The other way we could do this, instead of distribution of class by survival, we can look at the distribution of survival by class. So notice we're just switching them, okay? So now of all the first class people, what percent survived, what percent died, okay? Of all the second class people, what percent survived and died, third class survived and died, and crew, I almost said fourth class survived and died. And then of course, you could do the overall survival rate and the overall death rate. Ooh, death. That's depressing. I'm sorry. These are hard times for everybody. I legitimately was brought to tears like 20 minutes ago. I had to take a moment. I'm not going to tell you why. Personal matters. I'm a person? What? But math has got me excited again. So it's okay. Math is here to save your boring and sad day. COVID sucks, but math will make everything better. Sorry. Didn't mean to like remind you of sad things. Anyway, so if we graph out these two percentages, we have the survival rate, which is the one in blue here, and then we have the death rate, which is the one that's in purple. What do you notice? So same thing we're looking over here. Do they look like they're the same? Well, if all of these were level all across the board the same, then we would say that they would be likely to be independent. But notice there's also another trend. As the survival rate goes down, what has to happen to the death rate? The death rate has to go up because the sum of those two have to add up to 100, right? Isn't that cool? So really, we could just analyze one of those, either the survival or the death rate. Either way, we would expect them to be consistent across the board. Let's think of this another way. If your class did not change your rate of survival, okay, so what's the overall rate of survival? So if we go all the way over here, our overall survival rate would be 32%. So then if it didn't matter what your class was, what your ticket stub said, then what would you expect about all the distributions of survival or the survival rates for every single class? We would expect them all to be similar to 32%, which would be graphed about right about here. But the actual survival rates were lower or higher depending on your pay stub ticket. So 24% survival rate, 25%, 41, 62. We just graphed that. 24, 52, 41, 62. Okay. We also could have done the same thing just comparing the death rates as well. Okay. We're over here. The overall death rate on the Titanic was 68%. For the crew members, it was 76, 75 close, and then 58 and 38. Okay. So that goes down as the other one goes up. Really, really cool stuff. All right, independence versus association. So distribution of survival by class is pretty much exactly what I was talking about before. So if we graphed out all of those, I think on this one we're only looking at the death rate. We'll notice that they're not all the same. We would expect them to all be close to 68%, which would graph out a line. Actually, I can graph that line. Is it 4? Is it 3? Is it? Ah, I found it. So I could actually graph out that overall line, which is about 68%, about right here. So we would expect all of them to be even with that. Are they? No. So what would you conclude about the survival rates or about distribution in class? Are they independent, or does there appear to be an association? There appears to be an association. Why? Because the death rates were not even across the board. Okay, and you can see that visually, graphically, which is really, really cool. All right, so another way we can look at this. So this is going to be the distribution of class by survival again. You could look at either the alive or the dead, the distribution of class by whether or not they survived. Instead of breaking it down in a pie graph, which is hard to read the actual percentages, remember that, you could do something called a segmented bar chart. And notice it's going to go from 0 to 100%, and each segment's going to be a broken down percentage. Now, it's still kind of difficult to read what those percentages are, but it's just an alternative to a pie chart, and you get the same information. So what are we looking for? Over here are the areas about the same. The distribution's about the same. No, they're not. Can you see the same thing, maybe even easier? I don't know, it just depends. They're really the same graph. With the segmented bar chart, we would expect this orange part to be the same as this orange part, but it's not. We'd expect that green part to be the same as that green part, but it's not. Same thing with pinks, which are really close to each other, and the purples, which are not too far away either. The main difference would be the difference between the survival rates in first class and the crew members. Who would have thought? Kind of cool. Okay, so another one we're going to get into, sweet, we're only 10 minutes in, is smoking in education. So there was another question, I don't remember where they got this data from, it was from the book, and it was basically wondering, is whether or not somebody smokes, is there association between whether or not you smoke and your highest level of education? So did you only have a high school diploma? Did you go to 2-year college and get an associate's, or a 4-year or more from a university, like a bachelor's, master's, or a doctorate, right? They grouped all those together, okay? So we want to see if there's an association between these two. Well, whenever I look at the contingency table, so it looks like 32 total, it's a frequency, counts were smokers that only had a high school education. 61 people who were surveyed, I think they were coming out of a grocery store or something like that, or a mall, were non-smokers who also just had a high school diploma, et cetera, et cetera. Okay, just looking at these numbers, can you clearly see what's going on? Not necessarily. So what would you rather do? Graph it out and look at a graph, right? Whether when you do a segmented bar graph or a pie chart, or if you want to graph out just the rates going across either the columns or across the rows, it doesn't matter. You get the same information and you can still compare, which is kind of cool. So what I do here, I have the marginal distributions, which are like totals. So what's 32 plus, or sorry, 32 plus 61, 93, etc. So there were 93 out of the 200 were only had a high school diploma is what that means. All right, so what I want to do is actually want to break this down and use the percentages here. So first thing, I should have colored those, but that's okay. So 64% of all smokers, so I'm looking at this column here and the distribution of their education based on whether or not they smoke. So 64% of smokers had a high school diploma, only a high school diploma. 10% went to community college, and 26% went to a 4-year university or above, and altogether that would be 100%. Oh, I don't like it when it does that. Same thing with non-smokers, distribution of the non-smokers. 40.6 repeating percent went to only had high school. 11.3 went to community college, which is slightly higher than that one, than the smokers. 48% went 4-year or higher, which is almost double the amount from the smoking group. So the question I have is, do these two now, when we're looking at the percentages, which is easier to compare than the totals, right? Because now they're weighted the same out of a total percent. Now is it easier to compare? So 10 is close to 11, 64 and 40, that's pretty significant to me. And then 26 to 48, twice the amount. So if you're a non-smoker, it looks like the proportion was twice as high that you would go to a 4-year university or not. So yeah, those do not look like they're independent of each other. We could graph them out. I don't think I did. And I don't think you're doing it on the assignment either. Yeah. Aww. Anyway, no. You do it on the assignment for number 5. So I do want you to graph that out. And then based on the graph, you'll be able to make the decision whether or not you think they're independent with your visual data, which can be really cool. So I'm excited for you. Fun assignment. Let's be honest, the first 2 assignments, not that exciting. This one is dope. Yes, I said that. I learned a new word too, but I'm not going to let you know that I know these new words. Okay, so next one, contingency table for sex and political views. So fun stuff, right? This is actually the data from last year. I'm not going to use your data from this year because let's just say I wanted to keep it anonymous, and of course it's anonymous. I don't know who said what, but whenever I looked at your data, yeah, it would have been, there was a trend, and I didn't want you guys to see the trend because I didn't want you to possibly be able to know anything about your other classmates in this class. So this is last year's data because, politics is kind of angry right now at everyone. So we're going to use last year's data just to be close, but I will tease you with what I saw from this year's data, which was really, really cool. All right, so last year's data, it looks like we had 5 liberal men, 3 men who were moderate, and 3 conservative men, and 10 liberal women, 6 moderate women, and 3 conservative women. And then you see the marginal distributions on the side. So I'm going to go ahead and just break this down. So the first thing that when you're just looking at the data here, does anything look unusual? Does it look like there's any trend? Like, does it look like women are more likely to be liberal, or does it look like, yeah, that's a trend that I see actually. Does it look like perhaps men are more likely to be conservative, or overall, does it look like the group is more liberal from last year? What kind of trends could you see? And you could break it down. But of course, graphing it out is going to be the easiest way. So this next part that I'm going to show you is what we would expect if they did not have any relationship between. If there's no association between your sex and your political affiliation, what do we expect from this group? Okay, so let's see if we can figure out where these numbers come from. All right, so this part that I'm doing in red here, don't worry, I'm not expecting you guys to know how to do this. This is something that we're going to see in the very last chapter of the book, okay? So for just a moment, all the stuff you see in red here, just sit back, relax, and enjoy. If you can wrap your head around it, that's freaking awesome, because it's something we're going to do at the very end of the book. It's just something I wanted to show you. Just to tease you and see what we can use the power of statistics with. All right, so first of all, let's look. So we have 15 liberals out of 30 students altogether. So what do we know? What's the liberal rate? That's weird to say, but what's the liberal rate? It's 50%, right? So half of my students last year identified as liberal, which is kind of cool, right? And then 11 out of 30 were men. So I had 11 male students out of 30, and then half of them were liberal. So where did I get this 5.5 number from? Be really impressed if you get it. I'll say it again. Half my students were liberal, and 11 of my students were men. So if those two were independent, how many liberal men would I expect? Well, if half of all my students are liberal and 11 of my students are men, half of 11 is 5.5. Did you see that? So that's how we would find that out. So what we do is actually, in case you're curious, you can take the rates. So 15 divided by 30 times this rate, which is 11 divided by 30, but then you have to, that's an overall percentage, but then you have to multiply by 30 to get back to counts instead of a proportion. Another way you could do it is 15 times 11 divided by 30. Okay, again, I know, mind blown, crazy stuff, and you can tell I'm excited about it because it's math and it just makes perfect sense, right? But you don't need to know any of that right now. So let me just go ahead and fill in the rest of the chart so you can see what we would expect if there was no association. All right, now what I want you to do, back to you can do this part, is compare those numbers. How far is 5 away from what we expected, 5.5? How far is 3 from 3.3? 3 from 2.2. Those are pretty close. They're all actually really, really stinking close to what we would expect if there was absolutely no association. In fact, we can't have half a student, so of course it's going to be, that's the closest it could get, right? We can't have, half a, never mind. Anyway, so how unusual is this observation that we saw? How close is it to what we expected? It's actually really close, meaning it's a very common observation. So what would the percentile be? So the percentile, we would say that this observation was in the 75th percentile of what we would expect if there was no association, which would be an incredibly common, very, very normal to see of an observation. We're actually talking about p-value here, but you don't quite know what that means yet, so it's okay. I'm trying to use other terms. So we would not have enough evidence to say that there is any sort of association based on this between the two. But what's interesting is whenever I looked at our data from this year, I mean, your data, our p-value was less than 1%, meaning it was in the top 99 percentile of all observations. Meaning the data that I got from you guys was incredibly unusual, saying there were some definite trends in our class, at least, definite trends between whether or not your political affiliation based on your sex, which is crazy. kind of frightening. And that's why I'm not going to show you the data, because you'd be able to tell some certain things about a person based on their sex. You'd be able to kind of predict their political affiliation. So kind of meant for it all to be anonymous, but whenever I gathered the data, it was pretty unusual. And so I know something about you. Well, not you, but about the group. And it's really, really cool. Stats is awesome. Okay. I'm going to take a breath, calm down and get through the rest of this video. Oh, that is the rest of the video. Okay. So we are done. I hope you enjoyed that. I thought it was really stinking cool. There was one more thing I was going to show you. Okay, I was going to show you where I got the percentiles. So I'm going to get out my handy dandy calculator here. And you guys don't have them yet. I'm thinking maybe Friday, but don't hold me to that. I'll get the data as soon as I can. I emailed Brenda about it. And you guys will be able to come to the school. So I didn't say Friday because it's not official, okay, by the way. You'll be able to come to the school and pick up the calculator and the textbooks so you guys can have it for the year, which will be great. So let me just show you what I did. So second matrix, and then I have matrix A and matrix B. Okay, so it's the 5, 3, 3, 10, 6, 3. I'm trying to figure out what set of data I was looking at. So 5, 3, 3. Okay, yeah, it's actually this data right here. So I'm going to show you how I got the 75th percentile. So that's our matrix of what we observed. Matrix B is going to be what we expected, and those are going to be the red values there. Okay, so you can see that clearly. And then what I do is I go to stat, arrow to the right to test, arrow down until I get to the chi-squared test. Okay, not the goodness of fit, but just the chi-squared test. I know this looks crazy, but we're actually going to know what all that stuff means by the end of the year. I know, so exciting. Our observation is matrix A. What we expected was matrix B, and all we hit is calculate, and boom, it does it for us. You see that P right there? That's what we call our p-value, okay? And that tells us the percentile of our observation. So from last year, the percentile of our observation was the 75th percentile, which anything that's going to be higher than 5% or 10% or 1%, meaning it was not in the top 99 percentile or whatever, would not be considered unusual. So yeah, really cool stuff. And that's something we do in the very last chapter, and we're already showing you in the second chapter. So you don't need to worry about that at all for the test, or sorry, for the homework today. So all the stuff that's on this slide in the red, don't worry about that percentile. Don't worry about that like it never happened. And just do the homework. So the back side, you've got the homework problems that are from the book. When you have the book, all the odd problems, the answers will be in the back of the book so you can check them. But I do want you to work all the problems, even on the front page. Those are kind of the examples that we walked through. I want you to work all the problems that are on the assignment. All right, I'm going to stop talking. I'm pretty sure that's 3 days in a row that I made videos less than 25 minutes long, which is kind of my goal. So you're welcome. If I'm talking too fast, you can always slow it down for you with the playback speed and YouTube. Or if I'm not talking fast enough for you, you can always up the playback speed as well to get through the whole thing even quicker. So do your homework. If you have any questions on the homework, feel free to ask. And I will walk you through the solutions. I got the solution manual, so I will copy and paste the solutions for you in my own words so that I can walk you through how to do it. So if you're stuck and you don't know what to do, just ask. That's what I'm here for. And that's it. So see you guys. Have a good day. Stats is awesome.